Hi everyone, my name is Sruthy and I'm from Indian Institute of Science, Bangalore, India. In this video, I'm going to talk about our work on semi-grand free NOMA in frequency-selective channels with adaptive decoding that has been already presented in Globecom 2025 happened in Taiwan. So before going into semi-grand free NOMA, let's first understand what is grant-based and grant-free access. In uplink communications, in grant-based schemes, a user has to send a scheduling request to the base station before sending the data. And then the base station sends a grant towards the user, and then only the user can send the data. So it has reliability and control, but at the same time, it has access delays and signaling overhead. On the other hand, in grant-free access, there is no such control. Whenever a user has data, it can send immediately to the base station. So it has low protocol overhead and low latency, but at the same time, it has packet collisions. So in semi-grand-free NOMA, in semi-grand-free, we combine the best of both of these schemes. And in semi-grand-free NOMA, it allows both grant-based and grant-free users to share the same resources using power domain NOMA. So as shown in this figure, it's an uplink communication in which there is a grant based user which has been already scheduled by the base station. And let's say there are 4 grant free users and we have to select one among them to transmit along with the grant based user. So semi-grant free NOMA balances grant based access, reliability and control, and at the same time it has flexibility from grant free access with low protocol overhead and low latency. To implement semi-grant free NOMA in practice, it has to be compatible with the 5G 6G physical layer. The first thing is that it must operate over orthogonal frequency division multiplexing or OFDM. In OFDM, the system bandwidth is divided into physical resource block as we see in this figure, and each resource block consists of 12 subcarriers. And another thing is that we cannot assign arbitrary transmission rate to the users. It has to be constrained by a finite set of modulation encoding schemes levels that has been specified by the 3GPP standard. As we see here, we are listing a few modulation encoding scheme indices from the standard and their corresponding modulation like QPSK, 16 QAM, 64 QAM and their rates in bits per symbol. Here from this figure we can see that in discrete rate models a range of SNRs correspond to a particular rate, which is different from the continuous rate adaptation models that has been widely used in the literature. Another practical consideration is common modulation and coding scheme power constraint. What does that mean? In frequency selective channels, the channel gain across the subcarriers are different. And at the same time, the standard mandates that a common modulation encoding scheme and power must be used across all these subcarriers, even though they see different channel gains. It reduces uplink feedback and downlink control signaling overhead. Another important thing is the decoding orders in semi-grand free NOMA. This is uplink communication and the base station is the receiver and it has successive interference cancellation or SIC to retrieve data. There are two users, right? One grant free and one grain based user. And because of that, there are 2 decoding orders at SIC. So the first one is it can decode grant free users data first and then cancels out from the receipt signal and then decode grant based user signal without any other interference. This we call it as F2B order, and the other decoding order, the reverse decoding order, we call it as B2F decoding order. So for a given scenario, which one to choose? For that, we consider both these decoding orders and then we will pick the highest rate as the optimal one or the best one. So that we call as adaptive decoding order. And another question here to ask is that how to admit a grant free user. Let's say there are k grant-free users as we see in this figure, and we have to admit one among them. For that, we are defining a metric called mu k at each of these grant-free users, and we will say that the admission rule is that we will admit a user S with the highest metric mu k. So in our work, we are proposing the mu k, the metric mu k as the ratio of instantaneous rate of the user at time t to the average rate of the user till t minus 1 whole power alpha. Here alpha is the fairness level parameter, where alpha equal to 0 corresponds to max rate based, which has been commonly used in the semi-grand-free NOMA literature, whereas alpha equal to 1 corresponds to proportional fairness, the famous proportional fairness admission, and alpha equal to infinity corresponds to maximum fairness. So to find the metric at each grand-free user, we have to find the rate of that particular user at time t, right? For that, we are considering a system model in which there is a grant-based user and there are k grant-free users, and we are considering frequency selective channels, and we are using discrete modulation and coding schemes that has been given by the standard. We are also accounting for the common modulation and coding scheme power constraint that has been specified by the standard. Since the grant-based user is scheduled by the base station knows grant-based user's parameters such as the power, its channel, and its modulation and coding scheme that meets minimum rate constraint of the grant-based user. Okay, so our goal is to find the modulation and coding scheme and power for each grant-free user that maximizes its rate, such that we can find the grant-free user with the largest metric. So for each grant-free user, we have to consider both the decoding orders. As we already mentioned earlier, we have to consider both F2B order and B2F order in order to find the modulation and coding scheme and power. Okay, so let's consider the F2B order. So here it first decode the grant-free user signal, and for that the SINR expression on the nth subcarrier is given by the signal power of the grant-free user k divided by the interference from the grant-based user plus noise power, and then it cancels out from the total received signal and then decode the grant-based user signal without any other interference. So its SNR is given by signal power divided by noise power on the nth subcarrier. Similarly, we can define the SINR and SNR expression for the B2F order as well. Okay, so here the challenge is that since we are using frequency selective channels and we know that the channel gain across these subcarriers are different, and thus the SNR or SINR at each user is becoming a vector and not more than a scalar, right? So how to deal with this? For that, we are using a technique called exponential effective SNR mapping or EESM. EESM maps a frequency selective channel into a frequency flat channel, and it maps a vector of SNRs into an equivalent SNR in an AWGN channel that results in the same block error rate. To verify EESM, we are plotting block error rate as a function of SNR for different modulation and coding schemes. Here we are plotting the block error rate of each modulation and coding scheme in an AWGN channel, that is the blue curve, and the scatter plot is shown for the EESM. We can see that the scatter plot follows the AWGN channel, the blue curve with minimal spread, which confirms the accuracy of EESM. And EESM has been extensively used in 3GPP system level simulations. So using EESM, we map frequency selective channel into frequency flat, and thus we solve the problem. Okay. So we first consider F2B order. Here our goal is to choose optimal modulation and coding scheme and minimum power for grant-free user K subject to block error rate constraint of grant-free user and minimum rate constraint of grant-based user. To formally state this optimization problem, we write it as follows: maximizing the rate Rm Here M is the modulation and coding scheme that coming from the finite discrete set, and Pk is the power for grant free user K, which is continuous. Subject to block error rate constraint of grant free user K, we say that the block error rate should be less than or equal to some threshold epsilon. In practice, we say that 10% block error rate. And then there exists minimum rate constraint of grant based user, and then the maximum power constraint of grant free user. Okay, so how to solve this? Since M is a discrete variable, M can take only discrete values, we can say that this complete optimization problems becomes combinatorial in nature. And to solve this, we will take for each modulation and coding scheme, and we will check whether there exists a feasible power allocation that satisfy all these constraints. If it's yes, then we say that particular modulation and coding scheme is feasible, otherwise not. And among the feasible modulation and coding schemes, we will pick the highest rate as the optimal one. So to choose or to check the feasibility of a given modulation, before going into that, let's look into this equation. Here, the minimum rate constraint of grant based user is no more a function of pk. Why? Because in the F2B order, the grant based user is decoding in the final stage without any other interference. That's why. So here this equation or this constraint is redundant, we can remove it. So to check the feasibility of a given modulation and coding scheme, for this order, we are using a technique called bounding approach. In this approach, we find a bound on a bound on effective SINR of grant free user K. So this is the grant free user K SINR expression. Here we try to pull out this PK, the optimization variable PK, outside this involved form. So we will get the bound as follows. Here, the PK, the optimization variable PK, lies outside of the or becomes linear in PK. Okay. So using this bound, we will rewrite the block error rate constraint of grant free user as follows. So this constraint becomes linear in power PK. And thus we can solve this and we will find the highest rate as the optimal one. Okay. Whereas in the B2F order, our goal is to choose the optimal modulation and coding scheme and minimum power for grant free user K, subject to minimum rate constraint of grant based user and block error rate constraint of grant free user. Similar to the other order, previous order, we formulate the optimization problem as follows: maximizing rate subject to minimum rate constraint of grant based user, block error rate constraint of grant free user K, and then the maximum power constraint. Here, there are two constraints. Here, again, all these constraints are depending on pk. So we cannot avoid any of these constraints in this order. And moreover, that we can see that here ESM equation of the grant based user is as follows, and here the optimization variable pk is lying in the denominator, and we cannot use the same technique that we have used in the previous decoding order. So here we are using a method called law of large numbers based approach. In general, the number of subcarriers are large, and as n tends to infinity, we can rewrite the ESM equation of the grant based user as follows. Here we are replacing 1 by n summation as expectation. Okay, and we can find the closed form expression for this, and it will be a function of pk. Similarly, we will write the block error rate constraint of grant free user K also using law of large numbers. So using law of large numbers based approach, the minimum rate constraint of grant based user changes to the following. The block error rate constraint of grant free user K changes to this, and there exists a max power constraint also. So here we can see we can find the closed form expression for these expectations, and the expressions are in our paper. you can check. And from this, we can find whether you solving these four equations, these three constraints, we will check whether there exists a feasible power allocation, and thus we will find all the feasible MC modulation and coding schemes. Then we will pick the highest rate as the optimal one. So coming into numerical results, we are plotting to verify our approaches and algorithm. We are plotting average rate of grant-free users as a function of average SNR of GB user. So we are plotting the optimal solution as well, which is obtained from brute force numerical search across all the modulation and coding schemes and the power levels. So here for the F2B order, we can see that our proposed bounding approach achieves the same average rate of grant-free users as the optimal solution across all the SNRs and all values of alpha. Here alpha is the fairness level parameter, and we can also see that as alpha increases, the average rate, the fairness level, the fairness improves, and thus the average rate of grant-free user is reducing. Similarly, for the B2F order, we can see that our proposed LLN-based approach is optimal, and in our proposed algorithm, where we pick the highest modulation and coding scheme from both the F2B and B2F order, we see that it achieves higher average rate of grant-free users than F2B or B2F orders, and we can also see that the proposed algorithm is optimal for the adaptive order. So to conclude, we have seen that semi-grant-free NOMA improves connectivity and throughput, and it reduces delay. We have proposed a fairness-aware grant-free user admission and rate and power adaptation algorithm for frequency-selective channels with F2B, B2F, and adaptive orders. And our algorithm was in compliance with the common modulation and coding scheme, power constraint of 5G OFDM systems, and it can also be implemented in a distributed manner. That's all. Thank you for your attention.